So hello students. So today discussion is about radioactivity. So we already discussed about the nuclear reactions, the difference between chemical and nuclear reactions, yes or no, and what is how does a nucleus form and how does it happen, how does it disintegrate, everything we'll discuss in this video. First of all, radioactivity. What are radioactive substances? What is radioactivity? Students, listen. If the nucleus, in the nucleus, you already know the stabilities of the nucleus are depends upon mass defect factor, n by p, neutron to proton ratio, yes or no. All these are the factors for the stability. If the nucleus is not stable, then what will happen, students? The nucleus emits its own subatomic particles, or nucleus emits the radiation with enormous amounts of energy. That is called as radioactivity, and the substances which emit that radiation are called as radioactive substances. So radioactivity is the nuclear phenomenon in which a nucleus of an element changes into another element. Yes, sir, students. During a chemical reaction, one compound converts into another compound. During nuclear reaction, one element changes into new element. Why? Why? Because this time what are changing? Subatomic particles are changing, mainly protons. So by emitting the particles and rays and releasing tremendous amounts of energy, these substances that exhibit the property of radioactivity are called as radioactive substances. During this radioactivity, what is getting released, students? The subatomic particles, the radioactive, the radiation, as well as the rays, the enormous amounts of energy, all together is called as radioactivity. And the substances which emit this radiation are called as radioactive substances. So look at this. Mainly this was explained by the scientist Rutherford in a simple experiment by taking a lead block and having some radioactive substance, and when it is getting disintegrated, students, he placed one electromagnetic field with a positive and negative terminal. You can see clearly the rays which are coming from these radioactive substances. You can see clearly here, they are separated by three ways. So the ray which bends towards a positive terminal, that means it is made up of which charge? It is bending towards a positive, that means there is a negative charged particles, yes or no. And the ray which is bending towards a negative particle, that means by themselves it is made up of positive. And look at here, the straight one, it is not getting influenced by any of the ray, any of the terminal, positive or negative, that means that is made up of a neutral, yes or no. It's a neutral particle. So we have the types of radioactive particles: alpha rays, beta rays and gamma rays. Now you can answer, what are alpha rays? Positive rays or negative rays? They are bending towards the negative, that means they are positive rays. Beta rays, negative rays. Gamma rays, neutral substances. So we'll discuss in brief about these particles. Alpha rays have positively charged particles which can penetrate through the human skin. That's why these radiations are very, very dangerous, students. They can cause cancer, all the kind of radioactive substances. They can penetrate through the skin or paper, but are very energetic. And these rays can be considered to be the beam of helium atoms that lost 2 electrons, that is helium nuclei. Don't confuse. Alpha ray is nothing but the nucleus of helium. Helium nucleus contains how many protons? 2 protons. How many neutrons? 2 neutrons. How many electrons? Electrons are not present in the nucleus, yes or no. Helium atom contains 2 protons, 2 neutrons and 2 electrons. If that 2 electrons were lost, how can you represent the particle? He plus 2. Yes or no, it contains 2 protons and 2 neutrons. That is alpha ray. That is the simplest radiation. That means, is it a positive ray or a negative ray, students? Neutrons are neutral, protons are positive. So ultimately, what is the net charge? Positive only, na? Plus 2 plus 0. Understood? Neutron charge is no charge. Yes or no, students? So alpha rays are positively charged particles. There are no electrons here. That means an atom at a time it can release 2 protons and 2 neutrons, which is considered as an alpha ray. Understood? It's a positive ray. So that is also called as helium nuclei. Next, beta rays. Beta rays are negative rays, right? So beta rays are a beam of electrons. Obviously, what are negative particles inside an atom? Electrons only. So beta rays are a beam of electrons. The speed of these rays is slightly less than that of the light. What is the speed of the light? 3 into 10 to the power of 8 meters per second, right? But they are energetic enough to penetrate deep into the human body. So these are the high energetic electrons. Electrons are the negative charge. So beta rays are negatively charged particles. Alpha rays positively charged. Alpha is it only one proton? No, two protons and two neutrons. He plus 2 is alpha ray. Next, last one is gamma ray. Gamma ray is not a particle, students. It's a light radiation, contains electromagnetic radiation of high energy. So gamma rays are like light radiations in nature. They do not contain any particles. They travel with the speed of the light and can penetrate very deep into the thick concrete walls, sheets of lead and aluminium also. So these are the main rays, students. Most of the stars, neutron stars from the space which is coming, the rays we are cosmic rays, mostly they contain these gamma rays. So when the star is getting exploded, it releases this gamma that is also called as gamma burst. So it is a light radiation, contains oscillating fields of electric and magnetic with high energy, that is gamma ray. So once again, alpha rays are positive, beta rays are negative, gamma rays are neutral. Clear? So next, radioactive disintegration or radioactive decay, right? So when these rays, when any particular substance, when any radioactive substance undergo radioactivity, what happens? What are the resultant particles? How it is getting converted into? If an alpha decay is happening, how can you represent? If a beta decay is happening, if a gamma decay is happening, decaying means conversion, radioactivity is getting released. What is alpha decay? Alpha ray is getting released. Yes or no? What is beta? Beta is getting released. Got the clarity, students? So that is radioactive disintegration. So it's a process in which one nuclide is converted into another nuclide by the emission of alpha, beta and gamma rays. So first we have alpha decay. What is alpha? Alpha decay means losing two protons and two neutrons. Yes or no? You already know, sir, why they are losing. Still, if you have these kind of doubts, if any particle, why it is losing? Why? Because of the nuclear instability. Why there is a nuclear instability? Because what are the factors? Mass defect as well as neutron to proton ratio. Yes or no? If the proton repulsions are very high, a nucleus cannot withstand those repulsions. What will happen? It simply emit its own subatomic particles, and ultimately it will change into the stable state by releasing its subatomic particle. That is called as radioactivity. Understood, students? So look at here, alpha decay. When a radioactive nuclide undergoes alpha decay, it loses how many protons? Two protons and two neutrons. So the atomic number decreases by 2 units and the mass number decreases by 4 units. Yes, sir. What is atomic number? Number of protons. What is mass number? Protons plus neutrons. That's why atomic number decreases by how many units? 2 units. And mass number decreases by 4 units. Why? Because 2 protons and 2 neutrons. Protons plus neutrons is mass number. So look at one example is given here. Uranium-238-92. Isotope of uranium, when it undergoes alpha decay, it changes into thorium-90. Element is changing, remember. And mass number becomes 238 becomes 234. And this helium is getting released, He, 2 and 4. This subscript number indicates atomic number, superscript indicates mass number. Got the clarity about alpha decay, students? Next, beta decay. Beta decay is a beam of electrons, but here one concept is there here. Beta decay means not only electrons, or how electrons are getting released from the nucleus. Nucleus is unstable, right? How electrons, this is the doubt, right? Electrons are not get released from the orbital, students. A neutron is converted into proton and electron. What happens? A neutron break down into proton and electron. That means neutron is neutral charge, yes or no? It is made up of a proton, electron, proton positive charge, electron negative charge. So this neutron break down and released into proton and electron. This proton remain in the nucleus, but this electron is released as a beta decay, beta particle. Understood? Got the clarity? Ultimately, which particle is getting lost? Neutron is getting lost. Yes or no? In this neutron, half of the proton is there. Electron is getting lost. So that's how an unstable nucleus getting into stable form by releasing this beta particle. What is the meaning of beta decay? A neutron, the excess neutron present in the nucleus, break down to proton and electron. This proton remains in the nucleus. Electron was lost. Understood? So after this change, is there any change in the atomic number? Yes, there is a change. Atomic number increases or decreases? Atomic number increases by 1 unit. Yes, students? So some radioactive nuclides have a neutron to proton ratio that is too high. To reach the more stable state, they undergo beta emissions. In this process, a neutron becomes a proton and an electron. The proton stays in the nucleus, and the electron, which is and the electron, which is called as a beta particle, is ejected from the atom. Look at here, neutron converts into proton plus electron. This proton remains and electron is getting lost. During beta decay, there will be no change in the mass number and atomic number. Atomic number increases by 1 unit. In the nuclear equations for beta emission, the electron is written as, so this is how to represent the reaction, students. Iodine converts into xenon. This electron was released. So this is called as a beta decay process. So next, gamma emissions. Gamma emissions means you already know, light radiation emitting high energetic particles, yes or no. When a nuclide undergoes gamma decay, there will be no change in either atomic number or mass number because no particle is getting emitted. The excess of energy, what is happening during gamma ray? The excess of energy is getting released from the nucleus. Understood? Ultimately, in the beginning, in the previous video also explained, students, high energy means instability, low energy means stability. So excess energy is released in the form of gamma rays. So that is gamma ray emission. So students, emitted in the form of electromagnetic radiation. These are alpha decay, beta decays as well as gamma decay. So next, group displacement law. Group displacement law means if an element undergoes alpha decay or beta decay, of course gamma decay means there is no change in the particles, what happens, its position in the periodic table, whether it changes or not, that explains group displacement law. When a nuclide undergoes alpha decay, its position in the periodic table shifts 2 places to the left side. Yes or no? Alpha decay means releasing 2 protons. If it releases 2 protons, its position in the element changes, as students, ultimately its position in the periodic table changes towards which side? Towards right side or left side? Towards left side. Why? Because 2 atomic number atomic number can be reduces by 2 number. Yes or no? Atomic number reduces by the number of 2 protons. Why? Because 2 protons are getting released. So that's why the element in the periodic table shifts towards the left hand side by how many units? By 2 places, by 2 units. And if the nuclide undergoes beta decay, now answer, if it undergoes beta decay, does it happen is there any change in the position of its in the periodic table of that element? Yes. Towards the left side or right side? Towards the right side by how many units? 1 unit. Understood, students, right? So its position in the periodic table shifts towards 1 place to the right hand side. This is called as group displacement law, but it is not applicable for 3B group elements. 3B group elements means group 3 elements, students. Group 3 elements, mainly radioactive elements, comes under this F block elements. Yes or no? Group 3 contains 4F series elements as well as 5F series elements. How many elements are there? 14 elements are there in every series. Understood? All these 14 elements belong to group 3 only. In these 14 elements, if one element changes and another element, does the group changes? No. Yes sir, ultimately all the 28 elements of F block belongs to which group? Third group only. That's why it is not applicable for the third group element. So here we have examples given, students. So with alpha decays and beta decay, alpha decay, polonium, so 215, 84, it is changes into 2 units. It reduces by 2 protons and mass number reduces by 4 units. Yes or no? It is converts, alpha decay. Polonium converts into lead. Uranium converts into thorium. Radium converts into radon, students. Look at here, uranium to thorium. Uranium is a group 3 element. Thorium also group 3 element only. Total how many? 14 elements are there. 4F series and 5F series elements. So this group displacement law is not applicable for group 3 element. That means F block elements, you have to remember that point. So these are the reactions which comes under beta emissions, beta decay. Sodium converts into magnesium. So sodium belongs to group number 1. It converts into group number 2. Yes sir, no, the same element, if one proton is added, getting into the next position, which is group number 2. And francium converts into radium, which is group number 2. Group 1 becomes group 2. Look at here, thorium and proactinium. Is there any change in the group number? No. These are third group elements. Group displacement law is not applicable. So ultimately, during alpha emissions and beta emissions, what happens? Atomic number changes, mass numbers also changes. But during gamma emissions, particles are not changing. What is getting released? Students, what is getting released? Radiation energy is getting released. Understood? So that's how they get stability ultimately. So nuclear reactions, you already know chemical reactions, yes or no? And how to represent a chemical reaction? A reactant converts into a product. right? That is a chemical reaction. How to represent a nuclear reaction? Elements convert as a new element, either by releasing alpha decay, beta decay, or in gamma decay, no particle is releasing, energy is releasing, that's it. Understood? So here also we represent the same way how we represent the reactions, but in terms of atomic numbers and mass number, that is main. Why? Because ultimately subatomic particles are changing, yes or no, elements are changing, yes or no. You have to represent atomic numbers and mass numbers in nuclear reactions. Why? Because these particles only changing, right? So the equations that describe the nuclear reactions are different from those that describes the chemical reactions. Nuclear equations must clearly show the changes in the atomic numbers and mass numbers, sum of protons and neutrons in the nuclides. Ultimately, before the reaction, after the reaction, atomic number equal to atomic number, before the reaction equal to the atomic number, after the reaction, atomic number in the sense like I'm saying number of protons before the reaction are equal to the number of protons after the reaction, yes or no. The mass number before the reaction, that means number of protons and neutrons before the reaction are equal to the number of protons and neutrons after the reaction. Sir, how element is changing now? I'm not saying that the particular element, overall particles, for example, uranium 90 to 238 converts into thorium 90 to 234. I'm not saying to compare these two, compare everything. So 90 plus 2, how much? 92. 234 plus 4, how much? 238. Yes or no? Ultimately, overall particles are same. The particle is, uranium is changing into thorium, right? But by how it is changing? By releasing an alpha ray. If you combine everything, it is always anyway equal to uranium particles, 92 to 38. Understood, students? This is one point you have to remember while representing a nuclear reaction. What is the one thing you have to remember while representing a chemical reaction? Number of atoms on reactant side are equal to the number of atoms on the product side. And here for nuclear reaction, number of protons and neutrons on reactant side should be equal to the protons and neutrons on the opposite side, product side. Understood? That's the one point. So next we have half-life. The concept of half-life was introduced by the Rutherford. It is defined as the time required by a radioactive element to disintegrate into half of its original value. For example, 100 grams of radioactive substance is there, yes or no? From 100 grams to convert into 50 grams, how much time it will take? How much? What is happening? To convert 100 grams of radioactive substance to convert into half of its value. That means how much? 50 grams of its original value. How much time it takes? Whether it takes 3 days or it takes 5 days or it takes 1000 years or if it takes billions years, that time period is called as half-life. Understood? Only that much only? No, we have the second half-life also. That means 100 grams converts into 50 grams. For example, in 10 years, from this half again to convert from this half into another half. That means from 50 grams to 25 grams, how much time it will take? That's the second half-life time. And from 25 to 12.5 years. Yes or no? Sorry, 12.5 grams. How much? That is the third half-life. From there to their half value. So ultimately, all these are called as half-lives. Understood? What is the meaning of half-life? How much time it will take to completely disintegrate 50% of its original value. How much time it will take to disintegrate 50% of its original value. So it is defined as the time required by the radioactive element to disintegrate to half of its original value is called as half-life. So we have some examples, you will get the clarity. Listen. For example, radioactive carbon. Carbon 14 is a radioactive material, student, C14. So which decays to form nitrogen 14 by emitting a beta particle has a half-life of how much? Look at the half-life here. 5730 years. First half-life. And after 5730 years, one half of the sample remains. Yes or no? And one half has become nitrogen 14, right? Out of 100% sample, one half becomes nitrogen 14 and the remaining half becomes carbon 14 only. And this again disintegrate to the half of its value. So after 11,460 years, two half-lives, half of that remainder will have decayed to form nitrogen 14, bringing down sample to be 1/4 of its original value. Got the clarity? 100 grams, 50 grams, 25 grams, 1/4 or not, students? After 17,190 years, three half-lives, one half of which remainder after 11,460 years will have decayed to form nitrogen 14. So 1/8 of the original sample will remain. This continues with one half of the sample decaying each half-life. Ultimately, students, anything remains ultimately? No. This half-lives completely going on throughout in such a way that no sample is left. All the radioactive substances will disintegrate ultimately. Simply for our understanding, for our measurement, we are taking the half-life, half of it, from 100 grams to 50 grams, how much time it is taking. And from 50 to 25, second half-life. 25 to 12.5, third half, like that. Okay, that time period is called as half-life time. So students, we have examples. Half-life of tritium, what is tritium? 1H3 is how much? 12.5 years. This means that 100 grams of tritium reduces to how many? 50 grams in 12.5 years. Yes or no? Does it stop there? No. In another 12.5 years, 50 grams converts into 25 grams. In another 12.5 years, 25 grams converts into 12.5. Got the clarity? That is half-life. Half-life of uranium-238 is 4.5 into 10 to the power of 9 years. This means that 100 grams of uranium-238 reduces to 50 grams in 4.5 into 10 to the power of 9 years. So these are the examples of half-life. So the process of decomposition of radioactive nuclides continues until there is no significant amount left. Is there anything ultimately any amount left? No. This continues throughout. The whole radioactive substance can be converted into the most stable forms. So the length of the time necessary for a radioactive sample to decompose into the significance depends upon its half-life value and the amount of that particular substance present to begin with. That means this half-life value begins with the type of material, the type of substance, as well as the amount of the substance which it begins with. That is half-life, students. And this half-life, is it same for all the radioactive substances? No. It is different for different substances. So we have a graph here, half-lives and the percentage of radioactive position left. Initially we have 100 grams. Look at here, 50%. So look at the circle representations are given, 50% remaining, yes or no? And from 50 to 25%, 2 half-lives. This is 1 half-life, 2 half-lives. From 25 to 12.5, 3 half-lives. From there to 6.25%, that is 4 half-lives, and it continues. So 3.125% remaining after 5 half-lives. That means, is it left? No. That also undergoes disintegration. This is called as disintegration, not decomposition. Disintegration. That means a radioactive substances releases its radiation. Radiation means what? Alpha, beta or gamma. Converts into the most stable form. Students, got the clarity? So that's all about this alpha decays, beta decays and gamma decays. Remaining discussion about carbon dating we'll discuss in the next video. Thank you, students.